All right, here we go. So last time we finished the class and we finished the class talking about the different heat transfer modes, and we say we have three different heat transfer modes: conduction, convection, and radiation. Okay? We started to talk about conduction. Basically, I give you the relation here, which is equal to K A dt dx. K is what is related to the material, so different materials are going to allow the heat to go through it at different speeds or at different rates. So the more subjective is the material to transfer the heat, the higher the value of K. A is the exposed area, and dt dx is what we call the temperature gradient. Okay? So what will be the temperature between one phase and the other. And then we stop here and I say, okay, let me give you some values for K. So we have K for copper, which is 401, K for fiberglass. I think we're just writing a couple more. K for steel is 54. Okay? All right. So let me see what let's go to the next page. So let's go to page 15. Oops, no, doesn't matter. So page 15. Thermodynamics. Today is the 23rd, and this should be what, lecture 3? Yes, sir. All right. Okay, so let's just here recalling. The conduction equation, which is Q dot equal minus Ka dt dx. What I'm trying to find out is what would be the units. So what are the units? What should be the units for Q? Okay, so if it's energy, it's joules, but it's joules per unit time, no? So what is joules per second? Watts. Now A, that should be easy. What should be the units for the meter square? Now what would be the units for dt dx? What will be the units for t? What will be the units for dx? Meters. Okay. So now what should be the units then for k? You look, k will be equal to what? Will be equal to q or minus q divided by a dt dx. So what should be those units? Watts by meter Kelvin, no? Because the a squared will cancel with this one. All right, let us go to the next heat transfer mode. So we use for this one other nodes. Okay, so this is 1, 2. Would be convection. Okay, so this one is a little bit harder to explain now. It's not difficult, but because before a class that was called fluid dynamics was a requirement before taking this class. Okay, and what do we say was the medium necessary for convection? We say conduction will be for solids, convection will be for fluids or flow. So if you had some knowledge of fluid or flow, it will kind of help, no? Yeah? All right. So let me just give you the relation. So the relation is again, so mathematical relation. So again, is heat transfer rate. It's not energy. So basically, it's at the speed at which the heat transfer is going to go through a wall or through a medium is H times A. And generally, you write over here as delta T, or we can just write HA. So what is the direction generally of the heat? It's going from hot to cold, no? So we can go, it would be that direction here. Okay, so again, we can follow the same format as I did for the other one. Yeah. So what would be H over here? The other one was called the conduction coefficient. This one will be called I mean, now that we did it before, what should be the units for this one? Should be, what are the units for Q? Watts. What will be the units for A? Meter square. And what will be the units for temperature? So the units of H will be watts divided by meter square Kelvin, no? Okay, well, what is A? I mean, it's the exposed area. And that one is easy, units meter square. And what would be delta T equal to TH minus TC? That will only be the temperature difference. Okay, so before for conduction, we had the expression minus K times A dt dx, and we say that K was the conduction coefficient. So we went to the tables and found different values for K for steel, copper, aluminum, fiberglass, air, whatever you want, no? Okay, so what do you think about H? H now is what? Is it a solid or is it like a flow? So do you think we will be able to find values for H on a table? Let's think about it, okay? Example of convection could be if we had a fan in this room. So does it make any difference for the convection for the Q, okay, or for the H? Does it make any difference if you change the speed of the fan? Or it doesn't matter? It does matter, no? So basically it means that the H is already going to depend on what? On the velocity of the flow, no? Yeah? Now, do you think the material with which the blades of the fan are made will make a difference or no? I mean, I'm going maybe a little bit extreme, but does the surface or the finish of the blades will affect the flow of the air, no? Yeah? Okay? Basically, what I'm trying to say is that the convection coefficient, the H, is not a constant. It will depend on many, many things. So the first one, if you want, on the velocity of the flow, no? The other one, let's say if you need to remove heat from your skin. Will it make any difference if, I don't know, you are very smooth skin, or if you have a rough skin? Do you have hair on your arm, on your skin, or not? Do you think that will make a difference in order to determine the value of H? Okay? So you see there are different components or different aspects in order to determine the value of H. So obviously you won't be able to find the values of H in any table. Okay? If you want, try to Google it, convection coefficients, and you're not going to find it. All right? So that is what makes convection actually pretty difficult. All right? The equation is very simple. HA times the difference in temperature, but what is difficult to find is the value for H. Okay? So once you move to higher classes, you will see that for simple cases they have some empirical relations that are based on fluid dynamics, a class that you did not take, but basically based on numbers that are called Reynolds numbers, the Nusselt number, the Prandtl number, is all different numbers that characterize the flow. Okay? But again, you will see them, okay? I don't know if you see them anymore or not. But it's something very difficult. So that makes convection actually very difficult. It's not the equation. The equation is very simple, no? But to determine H is quite difficult. All right, so let me just write that. We're going to write that down. So page 16. The constant, the convection constant H is very difficult to obtain, for it depends on, let's say, flow velocity, surface quality, say smooth, rough, making convection a difficult problem. However, in this class, the value of h will always be given. All right, so actually people that do heat transfer or fluid dynamics, one of the main things they try to do is to find the value of h, okay? Many other simulations they do is in order to find h, okay, the appropriate h. All right, and the third one and last that we have is radiation. What do we say about radiation? Is that it requires no medium. All right. So that one has a couple of constants that I don't know, to tell the truth. Okay. So radiation. Okay. So let's say the mathematical. What did I say before? Relation would be what? dq dt equal to a sigma epsilon a t hot to the fourth t cold to the fourth. Okay, so we say radiation requires no medium. Okay, so from your class in physics, radiation will be similar to what type? I mean, how will radiation move in space? It will be on a wave form, no? So what else comes as a wave will be light, no? Okay, so light, heat is kind of related, all right? So since it comes as a wave, all right, there's that constant right here that shows up, which is sigma, which is called the Stefan Boltzmann, and that's always I have a problem spelling that one. Never know if there's one n or two n's at the end. It's 2n. Constant. And that one is equal to 5.67 10 to the minus 8 watt meter squared Kelvin to the fourth. Well, this is equal to 0.1714 10 to the minus 8 BTUs. I don't know why I have different units here. Strange. Okay. Hour, foot square, Rankines to the fourth. So again, these constants are constant that you can put into that page that I tell you can print with the units. Okay? If it's not there, you can put it. All right? I'm not going to ask you to memorize this. Something you can write on that page. Okay. So this one is related because it's a wave. All right? Now, epsilon over here is what is known as the emissivity. Okay? Emissivity coefficient. All right, and that one will always be between 0 and 1. So basically, this one, I don't know why they decided to call it emissivity, because the same thing that an object can absorb heat, okay, it can also give heat, no? So this could be called the absorptivity coefficient or the emissivity coefficient, no? Okay, so the assumptions that will happen is that writing down this equation, I'm not doing the derivation for you, but we're doing one assumption is that you're assuming that one object will absorb the heat the same way he will give the heat away, okay, of the medium. All right, so now, so that constant over here, the emissivity, has to do with the material, okay? So for example, what happens in the summer if you have a car which is black and a car that is white? Which one is going to be less hot inside? The white. Why? Because it reflects more light or it absorbs less heat, whatever you want to look at it, no? Okay? The black color will absorb more light, so it will not reflect as much light. So if you have leather seats, get ready for a burn, no? All right? Okay? So what's going to happen? So for example, if you have, let's say, low values of emissivity means that, that's why it's confusing. So low values of epsilon will mean what? It will be black or white? It will be white. High value of epsilon will be high values like the black color, no? Okay? So that's the reason. For example, what happened? Yeah, they still have them. And I think you still have them. Yeah. If you put your electric heater or electric cooker, no? When you cook. When you put it on top, what happens to the, so you see the coil, no? There is a coil under the crystal, or maybe you don't have a crystal on top, whatever. That coil is going to become what color? Red. Why? So first, those ones where you heat the coil, what is the main heat transfer mode that is being used? Conduction, convection, or radiation? Conduction. Okay, so yeah, it would be conduction once you go through the pan. Okay, but if you want, when you think about it, the heat we say is by radiation. Okay, is like light, is a wavelength. All right. So when you look at the light, the colors depends on what? On the wavelength of the wave. No? All right. So when you have the red, really is not that the metal is, yes, the metal is kind of going red, but is more like the wavelength of the air, which is outside, is going to the color red. Yeah? Okay? It's like, it's not like, but it's, sometimes people get a confusion. For example, if you have a guitar, what creates the music? Is it the vibration of the string, or is the air vibrating, like somebody said over there? Is the air vibrating? No? It's not the string vibrating. Is the string, yeah, it's going to vibrate, but it's going to change the wavelength in the air, which is what you're going to hear. Okay? So, for example, if you have, if somebody tells you what is the thing I would love to take to space, and you select to take a guitar, would that be a good choice? No, because it won't play, okay? So even though you think, oh, I want to play my guitar in space, it will make no sense. You will look like a fool, no? All right, so really what makes the noise is the wave of the air. All right, same thing when you have that red glowing. It's not that much that the metal is going glowing, it's because the heat is affecting the color of the wavelength of the light close to it. Okay? It is what is happening. So anyway, so we did, and the last thing we need here is A, again, is going to be the exposed area. All right, any questions so far? So we have done a lot of stuff, but we haven't do any example for this convection, for the conduction, convection, and radiation. So let's see if we can do a couple of problems. So 15, 16. Page 17, and let me go to find a problem. So I think this is chapter 2. All right, let's close this part over here. So basically, we defined all these equations the other day. Oh, they don't have the other ones. Okay. Push down. Oops. So most of the problems you will have here will be conduction. So let's do this one over here. I mean, you choose 247, 248. Which one do you want to do? 47, 48? 47. Okay. So 247 is over here. Okay, so you have the problem on the screen, so you cannot see what I'm going to do on the piece of paper, but basically what I'm going to do is I'm just going to recreate that figure over there, okay? So if you want, just say example 247 and then copy this figure, okay? And this is what I'm going to be doing. So example, problem 247. I'm going to copy that figure. So basically what is that figure? Is a thick, 6 inches thick exterior wall. So I'm calling the thickness L, okay, just to let you know. So the thermal conductivity of the material of this wall is K equal to 0.32 BTUs hour foot Rankine. Okay, they tell you that the hot temperature of the temperature on the left, T1, is 70 degrees Fahrenheit, and the temperature on the other side, T2, I guess that's what we need to find. I don't know. So T2, I guess that's the unknown. And then on the other side of the wall, what do you have? The outside, I guess air temperature will be 25 degrees Fahrenheit. And the coefficient of convection is 5.1 BTUs hour foot square Rankine. All right, so let's read. Steady state. Okay, so we need to determine T2 and the heat transfer mode per feet square. So we need to find the next. All right, let me go to the .com. Oh no, if I click there, I'm gonna kill everything. So I think I need to click here. Yeah. So this is what I've done. And now they ask you to find the heat transfer here going through the wall from hot to cold. What the units we were trying to is per feet square. So it will be per unit area, no? So these are the two things we need to find. T, the temperature of the wall on the cold side, and the heat transfer rate. Okay, I think last class we finished saying, can you stop the heat transfer? No, you can just slow it down. Okay? All right. All right, so okay, so let's first see what are the relations we have. So Q conduction is equal to what? dt dx, correct? Or I could just write over here Q dot over A. Conduction is equal to what? K of what? Where are we going? From hot to cold, no? So what do you have over here? T1 minus T2, or if you want to keep the minus sign, you will have to put minus final minus initial, no? T2 minus T1. But that way I get rid of this. Now, what is the other type of heat that you have on this area? So the heat goes by conduction through the wall, and then the heat goes from the wall into the medium air. Into what type of medium? Into what type of heat transfer mode? Convection. So we have Q convection is equal to what? HA delta T. So this will give you Q dot A convection equal to what? H of what? What is hot will be T2 minus TO, which is the temperature of the air, no? Okay, so then the total heat transfer that's happening over here should be equal to what? So will the total heat be equal to the Q that's going through the wall plus the Q due by convection? Or the Q going through the wall should be equal to the Q that is being removed by convection? What do you think is more logical? The first one or the second one? I mean, we said before that the amount of heat is not going to change. No, you can just slow it down. So the amount of heat which is going to go through the wall needs to be equal to the amount of heat you're going to remove from the wall by convection, no? Okay? So you can say that Q conduction will be equal to Q convection, or Q over A conduction will be equal to Q over A convection. So this is the important part. I mean, this one or this one, it doesn't matter. Either this one or this one is the important part in order to solve the problem. Because now you can write what? K T1 minus T2 will be equal to what? HT2 minus T naught. And now when you look at this equation, what is the only unknown? T2, no? So if we do some algebra, we should be able to solve for T2. Okay, so this will give you what? T2. So what do? We move T2, everything to the right. Okay, let's do, yeah, so this will be equal to T2. If I move this one to the right, will be H plus K. And I should move it to the other side, sorry for that. So now I need to move everything to this side. And this side I'm gonna have KT1 plus HT0. Yeah. So at the end, you're gonna have that T2 is equal to what? KT1 plus HT0 divided by H plus K. H plus K. All right, so let's see what will be the numerical application. So be careful over here, because if you look at K, what are the units of temperature for K? Rankine. So we need to move this one to Rankine, no? So let's do that first. So let's see. T1 equal to 70 degrees Fahrenheit will be equal to how many Rankines? What did we say was the unit transformation? Was it 460 or 459? 460, so we do 70 plus 460, which will give you 530 degree Rankines. Then we have T2 that we need to find, so we need T sub 0 or T sub naught. So 25 plus 460, 485 Rankines. Okay, so what do we get at the end? So oh, I did a mistake here, huh? Let's go back. I did a mistake here. Now I was looking at, okay, what is the mistake that I've done? In here, what am I missing? No, the dx, no? Yeah, so this is really divided by L, no? You see? Good that it's good, because then on the units we'll be able to find the problem. So this is going to change a little bit the algebra. This is K over L. So let's see, what is that going to give? T2, factor of T2 plus K over L equals to K over L T1. So basically what I need to do is, whatever you have a K, we divide by L. Sorry for that, guys. So let me just rewrite the expression over here. Oops, now. So we have T2 equals to K over L T1 plus H T naught divided by H plus K over L. Okay, so if we do the numerical application, what are we going to get? T2 is equal to what? 0.32 BTUs divided by hour feet degree Rankine. So that means that L will be equal to what? Will be equal to half a foot, no? So here you need to put 0.5, and T1 is equal to 530 Rankines here. And this is here by feet, okay? So I put the units, I need to put them everywhere. So now we're gonna space now. Plus H, what is the value of H? 5.1 BTUs divided by hour foot square Rankine, and here we're going to multiply by T naught, which is 485 Rankines divided by H, which is 5.1, more of the same, BTUs, hour foot square Rankine, plus 0.32 divided by half a foot, BTUs, hour foot Rankine. Okay, so if we look at the units, what's going to happen to the BTUs? Cancel out. What's going to happen? You have here foot times foot square, no? Foot square, you're going to cancel with all these foot square, foot times foot. What about the hour? Cancel out. So at the end, what is the only thing you have left? The Rankine, no? So this one, because this one cancels with this one cancels with this one, but this one will go on top. So this is good. So I don't know, what's the answer you get over here? So I know that I know the temperature needs to be higher than 485 degree Rankines. So again, I don't do the numerical calculations. I mean, I could look at the solution, but my goal is to go through the procedure, no? So you use your calculator, what do you find over here?
Yeah, 490.
490, that close? So somebody else gets the same thing? 490?
490.
Okay? So any question? So here, what's important is to recognize that the amount of heat going through the material is equal to the amount of heat being removed from the material by convection, no? This is important equation. Now, if we want to find what is the Q dot over A, how can we do it? We have two different choices, no? We can either calculate it using this expression, or we can calculate it using this one, since they have to be equal. Correct? So which one looks easier? Probably the second one, no? All right, so let's say second part, Q dot over A is equal to T hot minus T cold, which in this case is equal to what? T2 minus T naught, no? So Q over A is equal to H is equal to 5.1. Let's put the units one more time. BTUs per hour foot square Rankine times T2 we found to be 490 minus 485 Rankine, so Rankines are going to cancel. Okay, so that's correct. So at the end, how much do we find? 25.5. BTUs in international units is equivalent to what? No, joules. And that's why you have divided by what? By hour, no? Yeah, hour. And we are calculating this in function of what? Of the area, no? That's why you have left the foot square. Okay, so this was a good problem because we kill it with one shot, one problem for convection, one problem for conduction. Okay? So now we need to find one for radiation. Radiation generally are very easy, so basically they just plug the equation in most cases. All right, so what did I do in matrix 17? It's here, 17, 15, 16, 17. Page 19. Okay, so I see one 254. Let's see what that one says. A body whose surface area is 0. So let's do that one. So okay. So if you want weights, as I read the problem, and I try to make some type of sketch. So a body whose surface is half a cubic square, emissivity 0.8, and temperature, So temperature, I'm going to call it T surface equal to 150 degrees Celsius, is placed in a large evacuated chambers. Okay, so this is chamber whose walls are at 25 degrees Celsius. What is the rate at which radiation is emitted to the surface in watt? Okay. What is the net rate at which radiation is exchanged between the surface and the chamber walls? What? What is the rate at which radiation is emitted by the surface in watts? Okay. Okay, okay. All right, got it. All right, so I think I got it. We can check. Can maybe do a little bit of, oops, not here. Can maybe do a little bit of cheating here. So let me go over here. This is the figure that I did. All right. Okay, I'm going to do a little bit of cheating here because I think I know the answer, but I'm a little bit confused the way they answered it. So let me look very quick at the solution. I think the other thing they asked you at the beginning, the emissivity is just to multiply the sigma epsilon by the temperature of the body. But yeah, that's what they do, no? Okay, and then the second one, you just take the difference. Okay? Well, it is what I thought. All right, so let's do this. Oops. Okay, so first part is heat. So Q emitted by body. So we know is, so since there is no medium here, we know it's going to be radiation, so we know Q radiation. What is the expression? Sigma epsilon, and here will be what I call T surface to the fourth, no? All right, so again, I don't know the value, so in here we know that epsilon is 0.8, sigma was equal to what? 5.67, 10 to the minus 8 watts. Oh, I forgot something here. Meter square Kelvin to the fourth. Did I forget to put this one here? Yeah, I forgot to put the area, but I put it on the other one. So here you have the area. And the area we know will be 0.5 meters. So if you want, this one is okay, that is more clear. Okay, so we do the numerical application. What are you going to get? Q radiation equal to 5.67 10 to the minus 8 watt meter square Kelvin times 0.5 square meter. Oh, now we need to be careful here. What are we gonna have? Temperature in Kelvin. So we have T equal 150 degrees Celsius equal 150 plus what? 273. Would that be equal to 373, 423? So again, what you see here, this meter square will cancel this meter square. This Kelvin was, this is to the fourth. We'll cancel these Kelvins to the fourth. So we are just left with watts, which is what we want. Oh, I forgot that one. You see, I keep forgetting something. Yeah? Sorry for that, guys. 0.8. So what do you get at the end? $726. Is that what you told me? So 726 watts. Okay, so the next thing we need to find is Q radiated between body and chamber surface. So this time what are you going to have? Same equation, but you need to add the wall, no? So if we do the calculation as before, but I'm not going to put the units anymore because we know they cancel out. What are we getting? (5.67) 10 to the minus 8 times 0.8 times, we need to be careful, T surface is, we calculated to be how many Kelvin? 423. Now what would be the one of the wall? 273, let me put it here, plus 25, no? 298, yeah? And this is to the power 4 to the power 4. So this is over here. I keep forgetting something, huh? And times the area. So if you do this, what do you get? 527?
47.
547. Okay, so this object, if it was in space, it will radiate how much? 726. But let's say if you have it within a chamber with a body at a certain temperature, how much is going to be the radiation? 547, no? So you see that the amount of heat you can transfer or the amount of energy you can produce depends always on the difference in temperature between the hot and the cold reservoir, no? Okay? All right, so let me add some problems to the homework. So if we did this one, you're going to do 248. So 48 for sure. I'd say 46. $50. 55. We didn't do any of this stuff here. Huh. And let me add 63, and that's it. So let's see. Let me come here now. Oh, maybe I'll give you the heads up because I'm testing this stuff. Starting, I think, sometime in February or next semester, I don't know for you guys, you're gonna have to use a dual identification or dual identification. I don't know if you saw that one. So either you can use an app, because since I don't want to take my phone to class. I don't think it's good. I don't think it's a good example. Okay. Enter passcode, so they give me this token. I think it's February 1st, no? That's it. All right. So classes. So assignments. So you see, I keep adding problems. I think we can put a due date already. So we're going to put them at the beginning. 46, 48, 50, 55, 63. Hold on. Due date. Already February. Oh. So the first Thursday, week from today. So time will be anytime you want. I don't care that much. What I'm gonna do. Okay, guys, you can do it on any type of paper you want, but let's just do it this way. You won't have copies line, but let's do it online. File uploads. And what is the only thing you can upload? One file, okay? One PDF file. And that's it. Yeah, somebody had a question?
If we already did the earlier problems, do you care if our entire homework isn't in numerical order?
No, I don't care at all. I mean, if you did these 4 problems now, you can just put those pages at the end and the other ones at the beginning, okay? And if you scan it, it's not difficult to reorder. But I mean, it should not matter, okay? All right. So guys, another question. Start working on the homework. On Tuesday, I might do, if you have questions, 1 or 2 problems, not all of the homework, but some more examples. Otherwise, I'm going to keep moving forward, okay? So don't wait until... All right. Have a good day.